Okay, let me check. There is some delay on YouTube anyway, like 10 seconds. It's like 10 seconds delay, but we should be live. Okay, and I see we're live on YouTube right now. Cool. I'm really excited for today, guys. We've been waiting for a long time to have Marco with us, joining us for the GDG session. So Happy New Year to everyone. It's the first session in 2021, and we're starting with HTML, a very exciting topic. We want to say hello both from GDG Cloud Bydgoszcz and Warsaw. We're going to continue with our live session this year as long as the situation doesn't change and we can finally meet on site. So we're planning to have sessions every 2 months, 3 months, and we're starting, as we say, with HTML. The agenda for today is that we will have session with Marco, and after that we can hi Marco. Marco will introduce himself just in a second. And we're going to have the session of Marco, and after that we can have a Q&A session as well. So if you have any questions, please put it in the chat. I'll be looking for them, and I'll pass the questions to Marco in the end of the presentation. And also, guys, please pay attention to the presentation because we're going to have a contest at the end. So we'll ask you a question related to Google ML. And you can actually win this hard copy of the book preparing you for the GCP Architect exam. This is sponsored by Atos, so thanks a lot for sponsoring this. And yeah, I think we can start. So we'll give you floor, Marco. We're moving away. And yeah.
All right. Thank you, and hello, everybody. Greetings from Tokyo. My name is Markku. I'm a solutions architect at Google Cloud. So what does a solutions architect at GCP or Google Cloud do? Well, I work in the APAC region, Asia Pacific region, out of Tokyo. And my work is basically to help anybody who wants to use Google Cloud to use it properly. So customers, startups, students, anybody who is interested comes to us with problems and ideas, and they would like to make something like a chicken detector. And can it be done? Usually, yes. And then my job is to try to help them use the services correctly. And then quite often I create prototypes. So if a customer comes over with some ideas, I personally believe in seeing is believing. So it's easy to make slides. Everything always works in slides, but then if you can actually demonstrate at least an MVP, like a mini version of what the customer needs, then usually that's good. And then the second part is that as I build these prototypes, as part of our work as solutions architects, we are also then publishing solutions. So then you may see at Google Cloud web pages, we have some examples, tutorials, solutions, how to build certain things. And some of those are made by myself and my colleagues. And then the third thing I do nowadays is then I do some small YouTube videos for Google Cloud where I show live demonstrations in a video recording of these solutions and prototypes. Anyway, then my main work area is IoT and machine learning. And that's, I think, why I'm here. So I'd like to talk to you about this topic you should see on the screen. Edge AI with Google Cloud and Coral, which is Google's Edge AI hardware. So let's get going. And this is not just a death by slides, so I will have some live demos for you here as well to keep it interesting and real. But I have to show you a couple of slides to set the stage. So as Google, we have been doing Edge AI actually quite a long time already. You may know about Waymo, which is the new-ish name for Google self-driving car. So that's actually a great example of an Edge AI thing. So with the self-driving car, you have a physical world device, an IoT device, which has AI inside it. Because for the self-driving car, it uses AI to have understanding, visibility of the world around it, of course. And then it has to make millisecond decisions based on the information it gathers from all the possible sensors around it. So it's running on AI, of course, in the car, in the edge, and it has to run fast and it has to be reliable. So I personally think the self-driving car is like one of the extreme good examples of edge AI. And of course, you may know Nest is one example, AI-based IoT devices for your home. And then, of course, Google Home or Nest Home now. So again, IoT devices powered by AI. And then ultimately with IoT, I personally think that the kind of real IoT devices are quite cheap and quite small. Something like microcontrollers. The cheaper, the better, because then the IoT hardware is usually not differentiating. Usually it should be cheap because you may have thousands, even millions of them if it's a consumer device. Cheap means that it doesn't have a lot of processing power usually. It's constrained in many ways, including networking, etc. So then you need to help the device. And ultimately, it's all about the data. So IoT devices typically do two things. They have sensors and they have actuators. Sensors are obvious, so different kind of sensors to send the world around it. Like if it's a coffee machine, it has a temperature sensor, maybe water level sensor, etc. Some other machinery have vibration sensors. Then you might have fancy ones like cameras or LiDAR or ultrasound, whatever, sensors. And then actuators move things around. So some of the IoT devices can maybe move on their own, like drones or rovers. They have motors. And even more simple things like the coffee machine has some switches, motors, relays, etc. that you can use to manipulate the world around you, like start brewing coffee, open the door, etc. But again, IoT devices are supposed to be simple and cheap. They can barely have enough capacity usually to read the sensor readings, send the sensor reading data somewhere, like the cloud, and then receive some commands to start the motor or move the motor to a certain angle. But then if you use other processing to help the small device get a better understanding what it should do, then that's good. And why not use the cloud? Because the cloud has a lot of power. Imagine all the Google data centers, they are pretty huge. So one way is by connecting the cloud to the IoT devices. But then that requires a constant internet connection. If there's very heavy data coming from the device, like video, images, audio, or super high frequency sensor readings, then the internet connection may become a bottleneck. It may become expensive, like streaming 4K video or 2K video up, cost quite a lot probably. And the constrained device may not have the bandwidth for that or the connectivity, and the cost may become an issue. So there's many reasons why actually running AI on the device itself is helpful. Also, you want it to work offline. You may not want to be dependent on a working internet connection. If the internet goes down, you want your systems to still work, because the IoT devices are usually supposed to be helpful, helping the people, making their life easier. You don't want them to go offline, stop working if the internet connection disappears. Then how do you get AI on these little devices? Well, the interesting thing about machine learning is this, that machine learning is not procedural programming like we are used to in the old days. What I mean by that is we are used to programming things if the data, input data looks like this. If my data is that, then do that, else do something else. That doesn't really work anymore when you have things like video and images, audio streams, high frequency multiple sensor readings. You can't anymore really program this kind of if then else case logic. Machine learning models learn in a similar way as the brain by being exposed to the data. And then you can help the model a little bit focus on the right kind of data. I will show an example soon. But ultimately, then the model is running in a neural network and it learns from training data. So you give it examples of data, and often it's helpful if you can label the data that these are large chickens and these are small chickens. pictures of big chickens and small chickens. I will come back to that. Why is he talking about chickens? You will see some chickens soon. There's one here. And then you train the neural network with this example data, and then you go into production, so-called inference, by giving it new data. And then the neural network has learned the patterns in the data, and then it will recognize from this new data, what is it? So there's different types of neural networks. There's binary classification. Is it this or is it that? A or B, 0 or 1. Then classification of multiple labels. Is it a chicken? Is it a cat? Is it a dog? Is it a frog? Object detection is another one, which then combines classification and where is it in an image, for example, there. Then you have image segmentation, which is fancier, where you know that these pixels in the image belong to the frog. These pixels belong to the chicken. Anyway, moving on. That's machine learning. So you train the model. And usually you want to train the model in the cloud because we have the massive data centers in Google. They have the specialized processors called TPUs, tensor processing units, that we use for all the Google services that use AI. So you can use the same TPUs then for training your own models. And then we have services to make it easy to train these custom models. My favorite is the family of AutoML services, where you simply literally give your example data and you tell AutoML, please be so kind and make a model to detect some chickens for me from my data. Then you don't need to know how to make a machine learning model. It's literally machine learning as a service with AutoML. So I like that because I don't know how to create machine learning by hand. So say you do this and you create a machine learning model. How do you run it at the edge? Edge means the physical world devices. Well, that's why Google has a quite new family of products called Coral. It's a platform. So it's hardware products and software platforms, open source, of course, and SDKs, etc. A comprehensive platform for developing edge AI and then running it in production. So what is Coral? Coral, then combined with Google Cloud, lets you do end-to-end edge AI, where you probably want to use Google Cloud for training the data, hosting the data, doing other things with your data, running your applications there. Once you have trained the machine learning model from your data, you can export the model to a Coral device. So Google Machine Learning Accelerator device that you can either connect to your device or even embed inside your hardware if necessary. Why? Well, there are some reasons here why you would want to run machine learning on your device. One of them is privacy. There are many use cases, maybe medical, etc., where sometimes you just cannot send the raw data, the input data out of the facility or the country or the campus area, whatever. So maybe even from the device. So if it's a security camera, etc., maybe the raw data that can show some sensitive information cannot leave the camera. It just can't. So the cloud is not an option then for production because you cannot legally send the data there. Latency, self-driving car is a good example. If you need to make millisecond speed decisions, you cannot wait for maybe 100 milliseconds, 50 milliseconds for the cloud to send you a response back. Bandwidth, like I mentioned earlier, streaming high-resolution video would take huge bandwidth, and that's also quite expensive. So it may be better to just analyze the video stream next to the camera, even maybe inside the camera, and then just take actionable insights, results from the camera. So the video stream actually never leaves the camera in this case, much more efficient networking-wise. So then if you scale to millions of cameras or millions of IoT devices with high data volumes, the high data volume never leaves the edge, never leaves the device. Like I mentioned earlier, you want your things to work offline as well, probably, even if they lose the internet connection. And cost, well, you can make the devices then very small and cheap, because you can also offload the quite heavy machine learning processing to a specialized machine learning chip, like this, the Google Edge TPU. So the Google data centers have the large TPUs. I don't know how big they are, rack-sized. Haven't seen them in real life. The large Edge TPUs are running then Google's AI services, and you can use them when you run your AI models in the cloud. But if you want to run them on your device, Google Coral have made the Edge TPU chip, a tiny little chip that you can then embed to your solution, even inside your hardware. That's a machine learning accelerator that can run a TensorFlow Lite model, your custom machine learning model that you maybe train with AutoML or other services in the cloud. Then you take the trained model, you put it on the chip, and you run it on the device. So let me show you what these Coral hardware look like. So here on the table, you can see a family portrait of Coral hardware that I happen to found here in my closet here. So from prototyping to production order, let's say, first we have the Coral development board that I'm trying to highlight here with the pen. So the Coral development board is a very popular and handy way of starting to use the Coral hardware for developing machine learning solutions and prototypes. So it's something like the Raspberry Pi 4, but it's not a Raspberry Pi, it's made by Google, but it's similar. So it's got a 4-core ARM CPU, up to 4 gigabytes of RAM, gigabit Ethernet, USB 3, USB-C based power and data, HDMI out, Wi-Fi 5, Bluetooth, BLE, etc. And under the heatsink is then the ARM CPU and the Edge TPU. So that's a all-in-one solution for developing, prototyping machine learning things, and it's running Mendel OS, which is a derivative of Debian Linux. So it's basically a Debian board. Then we have the quite new one, Coral DevBoard Mini here, and it's similar to the big one. It's smaller, as you can see. It takes less power consumption. It doesn't need a heatsink, anything. It's passively cooled. Otherwise, it's very similar. So you can maybe think of it like Raspberry Pi 4 is the large dev board, of course, with the Edge TPU. And this is more like a Pi Zero, this DevBoard Mini. It's cheaper, smaller, and especially lower power consumption. Then we have the USB accelerator, which is very handy if you want to add the Edge TPU to existing systems with a USB port. So there's a USB-C plug there. It works with USB 2, but preferably USB 3 for the higher bandwidth and faster, smaller latency from your Linux host to send the data. So you will be sending the data like an image here, running the machine learning model here on the Edge TPU, and then getting back the results, machine learning inference results. Okay, moving on. So those are prototyping boards and the accelerator plug-in with USB. Then for production, I have two versions here. I have the Mini PCIe, Coral Mini PCIe, and the M2 form factor. And the M2 is a dual Edge TPU, so there's two inside there. So these are then something you can embed to, for example, industrial PCs with M2 or Mini PCIe expansion slots. Then we have a couple of other expansion ports that are related to the family. Here we have the Coral environmental sensor port. So it can attach to the 40-pin connector on either one of the development ports. And then it adds multiple sensors, environmental sensors, temperature, humidity, there's a light sensor, there's an OLED screen. And the Grove connectors, there's multiple digital and analog Grove connectors. And there's a GPIO button as well. So it's a handy way of then testing sensor readings, maybe passing them through the machine learning model using this sensor board. And then last but not least, from Sigfox, our technology partner, we have the Sigfox MRQ board, which is a radio module. So this is also something you can attach to the 40-pin expansion slot here. And it adds an LP WAN radio connection using the Sigfox protocol and network to the Coral development boards. So with this one, then you have an LP WAN connection in currently 73 countries with the Sigfox network. All right. So that was a quick introduction to Coral hardware. What can you do with those things? Well, let me show you an example. This is a screenshot of one of my YouTube videos. About a month ago, I published this episode. So when I got the DevBoard Mini, this one here, I needed to make an example of that. And it also has a microphone on the board. So the example I made is voice control running voice recognition locally on the DevBoard Mini. So all you need is this DevBoard Mini, there's a microphone, there's the Edge TPU, so it can listen to your speech, run a speech recognition machine learning model on the board, on the Edge TPU, and then you can react to that. And the solution or prototype I built for this is controlling my lights in my study/studio here. So as you can see, I can actually press a button. So I have Python controlled lights in the background there. I can switch them on and off. So what I'd like to do then is to have voice control with the Coral DevBoard Mini, detect what I'm saying, and then send a Python command to my lights. So this is the architecture here on the screen. It's super simple. There's a human, me talking. There's a microphone on the DevBoard Mini. It hears your voice. You pass the audio stream from the microphone to a Python app. In this case, I only know how to code Python anymore. And then you analyze the audio stream with a machine learning model that's for speech recognition running on the Edge TPU here. And based on the results then, the Python code is calling the APIs of my lights. So without any further ado, let's see if that works. So let's now try a live demo of this. So this particular one, because my DevBoard Mini is on the table here, I run this demo app now on my iMac using this USB accelerator. So in practice now, the second one that's connected, in practice now, the demo I will execute now uses actually this Coral USB accelerator. That also shows that then when you make a prototype or solution using these Edge TPUs, you can change the form factor. So I developed this demo with the DevBoard Mini. So this one, but because it's not connected anywhere now, it's not working. So I can run the same exact app on this USB accelerator using my Mac as the host. So let's do that now. So very simple thing. You can see on the screen here that I'm in the directory of this demo app. The demo app is called keyword execute something detector. And I will tell it to use the iMac's built-in microphone for the audio input here. What did I do? Here we go. All right, let's start the app, and then microphone 4 should be okay. So now if I say switch off, it switched off the lights. Let's try again, switch on. And I've also taught or selected a couple of other keywords. So see, hands off, not doing anything. We can say turn up. So that you can see on the screen. If you look at the console there, you can see that it detected turn up. I did it again. And that uses the script then to send -- up, which maximizes. Let's go down, turn down. Now it minimizes the lights. And if I want to go back to the default setting, I can say, what was the keyword? Position 11. Yes. So let's try one more time. Switch off and switch on. Yay. So, okay. So again, that was a live demo using the Coral USB accelerator in this case, but the same exact app I was running on the DevBoard Mini earlier. All right, so that worked. Voice control, locally running voice control. So let's move on. Then I'd like to show you a real customer case. So that was kind of a silly little prototype that I developed as my first app for the DevBoard Mini. This, on the other hand, was an actual production customer case here in Japan. So I'm based in Tokyo. The customer in question is Kyocera. They are a very traditional, very old company manufacturing, for example, ceramics, and they manufacture components for other companies as well. So small, medium, large scale production of components for other customers. They wanted to do visual inspection of their components on the production line. Traditionally, this is done by humans looking at them. It's very labor intensive. It's hard for them to train and find experts as the workforce is getting older to replace the older experts. And it's not fast and it's not accurate with humans. So Kyocera came to us asking, could we use Edge AI with Google technologies to not replace the people, but to automate this task so that the humans can do something else? They can focus on making new products, for example. So let's see. These, what you can see on the screen, are some of the actual images from the Kyocera production line. So they have a camera pointing down. The objects are passing on the production line. They are on a tray. You can see that the objects are jumping around. So there's many problems with this source data. These are the source images, literally. What we are supposed to detect are there blemishes and defects in the middle object here? You may see that little black dots are jumping around there. Those are actually faults. They are known faults. These are known to be bad component examples here. But there's many problems here for machine learning because the object that we are trying to analyze is jumping around and even rotating. So at first, when we tried AutoML just with these raw images, the results were not that encouraging because the machine learning model didn't know where to look. It's very confusing. Things are jumping around. So the worst case scenario, machine learning accuracy was only 14%. So that's not good at all. So then I took on the task as kind of an engineer to try to improve this and see if it would actually work for Kyocera. So I tried to do pre-processing. What if I pre-process the data before we train the machine learning model, and I help the AutoML model training by letting it see better the problem in the data? So these are the steps that I took. The first one was just to crop, just to cut the image. If I cut the image here, in all the example images they gave us, I was sure that I am not cutting into the main object we are supposed to look at, but I'm cutting away the unnecessary other objects in the edge of the image. Okay, so simple crop. So I just use Python simple image library for these steps. By the way, there's a defect. So ultimately, the machine learning model is supposed to detect, is there a problem, like a defect like that there. Oh, let me remove myself so you can see better that one. So the defects are very, very small. Next step that I did was to remove the background pixels. So I applied an image filter that changed the contrast and colors, etc., until the background of the object turned all black, which means 000 pixels. So those pixels have no value. Conversely, the only pixels remaining in this image file that have value belong to the object. Okay, so that's easy. Now I know where the object is. Then I can apply another simple image filter, which is just an edge detection. Because now the background pixels are 000, it's easy for the edge detection filter to then apply to know where the edges are. However, the edges are not lines, they are point cloud. So how do I get to lines, more accurate lines of the edges? By applying something called Hoff transform, which is then able to take this point cloud of dots that seem to follow a line and actually say that, yes, those are lines. So then I got these lines. Why did I do that? Because you may notice that the object is rotated. It's not flat. It's not horizontal. I wanted to remove the rotation by doing this Hoff transform, getting these lines that are corresponding to, in this case, this rectangular object, and I could calculate the average rotation angle of these lines. And I also removed outliers. You may see here that the third from the top line is an outlier. It doesn't agree with the other lines. So I removed the outliers, I averaged the others, and then I simply counter-rotated the object back minus, so negative that angle. So then the object became flat or horizontal. And then I simply did one more object edge detection and then cropped exactly on the edges of the object. So then we were left with these object images that are significantly better for AutoML training. Let me show you what it looks like. So see, after the pre-processing, we got these images, which are just the object. So now the blemishes kind of jump out. So either the object has those blemishes or it doesn't have those blemishes. And let's go to AutoML. This is the actual Kyocera training AutoML. And here we can see that after pre-processing, I uploaded these images to AutoML, and we can see examples of the known to be good images and known to be bad components, which have flaws. So you see those little dots there, like there and there. Then I simply press train in AutoML. We trained the model, and then I evaluated the model. And then here it's saying 100% accuracy. So I was very, very happy with that. So it was, model is saying with the initial testing that it did, using the sample data set, 20% of the images, it was able to 100% accurately classify between broken and good components. But I wanted to do a real test. So then I exported the model from AutoML to Google Coral HTTPU. Like this, I just selected Coral as the export target. I got the TensorFlow Lite binary compiled model file and labels file. I put it on this guy, exactly this Coral dev board, and I executed then performance and quality tests, and these were the results. So after we pre-processed the input data before model training, then the actual results were 95 and 98% accuracy for image classification for Kyocera model, and this was significantly higher accuracy than humans, and also the speed around 9 milliseconds is of course a lot faster than humans could do this quality control. So that was an actual customer case. And by the way, I can show you one thing here. Give me a second. Here you can see the interim outputs of the pre-processing. So I just executed in a debug mode this pre-processing script. That's the rotated image, and then this is the final one. So these final images I then put to AutoML and got the model, and I executed the performance test, and these are the results. So that was a real customer use case. And then finally, I'd like to show you another example where I built a prototype based on a customer request. So this one is related to smart farming, or using AI to help traditional agriculture and farming. So this particular customer wanted to have a chicken classifier. So they came to us with a problem. Could we use Edge AI to detect the size of chickens? So after the meeting with the customer, I went to an online shop and I bought some chickens. Not real ones, which would be very noisy, and I had to feed them and everything, but these fake chickens. And I used AutoML to try to create a chicken classifier. So you can see here the AutoML UI for the chickens. So I bought 3 chickens. There's a small, medium, and large chicken. Very small differences actually between those. It was even for me hard to see the difference. I was a bit skeptical if machine learning can actually be used to train a model to classify between those. Anyway, I took pictures of my chickens. I put them to AutoML. I trained a model. And then when I got the model out, then I again was able to export this model. So you can deploy the model to cloud production. You can export it to HTTPU as a container. You can run it in TensorFlow JavaScript on a browser, etc. So let's now see what happened when I made this chicken classifier for the customer. And then before I show you the live demo, let me show you the actual use case idea here. How is Edge AI useful? So say you have a farm, and at the farm you need to know what's going on. For example, how big are your chickens? Are your chickens healthy or not healthy? Or many other things. So then you may have some CCTV cameras, etc., looking at it, and you want to automate it with high accuracy. So let's say your CCTV camera is looking at the farm animals. You want to classify and maybe count them. So then you train this machine learning model in the cloud, and then you put it in the camera or server next to the camera. And then the beautiful thing is that the camera images never leave the farm. So you attach the machine learning accelerator to the camera. The camera looks at the world. the camera images are passed to the edge TPU connected to the camera. And then you take the inference results. How many chickens I see, how many are big, how many are medium, how many are small, maybe where are they in the picture. And then you send this simple semantic, highly actionable result data up to another system like a cloud backend and a monitoring dashboard, etc. So you never need to transmit the heavy images or video stream. And you also protect privacy. You're never transmitting any images that might, for example, have pictures of humans there. You're just transmitting some numbers, like 2 small chickens, 5 medium chickens, and 11 large chickens. So you transmit 3 digits. That's it. But it's also highly actionable data. You don't need to process it anymore in the cloud. It's already done at the edge. Then you can just take actions based on the data. All right, let's see the chicken classifier. And this one is running on my second Coral dev board. So here's the first one. The second one is running this demo. So on the table here, I have, let me actually turn the camera and try to show you. Give me a second. This might turn into a disaster, but let me try. Yes. So there's a chicken being a model. There's a webcam connected, looking at the chickens, and then the webcam is connected to the Coral development board there. Okay. So that's the physical setup. And then here we are on the operating system shell of my Coral development board. You can see it's Mendel, so Debian Linux. And when I start this demo app, it's going to then start analyzing the webcam feed and running it through the chicken edge TPU model. And let's actually see what it looks like. This is the Coral dev board's X11 graphical user interface. So as I start the demo app now here, we switch to the X11 interface, and here we go. So this is now what the webcam can see. So you can see on the top left that it's running the chicken edge TPU model. Interesting thing on the bottom left is then the inference time, 4 milliseconds. And currently it's running at about 220 frames per second. So pretty fast. And the input size is 720p, so 1280 times 720. So relatively high resolution in the camera. And then let me hide myself so you can see better. You can see that currently the model is saying that's a large chicken. But if I now move the small chicken in front, you can see it says small chicken and large chicken, small chicken. Sometimes depending on the lighting, it may have some small issues, but you can see that it's able to switch between the medium chicken, preferring the medium chicken and now the small chicken here. There we go. And actually the differences between, now it's better, the differences between the large chicken and the small chicken are very subtle. So I'm actually impressed that it's able to do this classification between the large and the small chicken. Now, of course, this is just a quick example, first prototype, but even this first prototype was able to successfully classify with a relatively okay accuracy between these 3 types of chickens. So there we go. That was the chicken classifier live demo. And again, here the use case then is that you never need to send the images or video feed out of the farm. Maybe the internet connection is very limited, very cheap. They only send extremely small data that, for example, they could use LPWAN for that, or NB-IoT, or simple mobile SIM connection. Quite often farms only have some mobile SIM connections for internet. Sending inference results like 3 digits, 3 bytes, or even 1 byte is nothing, right? So that was the chicken classifier. And that was running on the Coral dev board. Okay, here we go. There we come to the end of this presentation. I hope you enjoyed this quick look at building edge AI solutions with Google Cloud, mostly for training the models and then exporting the model to Coral devices that have the HTPU machine learning accelerator. And then you saw 3 examples of actually using this, couple of prototypes, and one of them was a real customer use case. So with that, I will hand back to Konrad then. Thank you.
Thanks, Marco. That was super interesting. I love the presentation. I guess people are not asking questions because they've been concentrating on what you're talking about, because it was so interesting there. So can we sum up really that you don't actually need to be a data scientist to Edge ML?
Yeah, absolutely. I am not a data scientist. So shameful truth, for the last 4 years, I've had a to-do list item in my own to-do list, learn TensorFlow. I still haven't done it. And now I'm thinking I don't really need to and want to anymore, because we have services like AutoML that can just automate it. So Cassie Kozyrkov from Google, my colleague, she always says, you don't need to know how to make a microwave oven, you just want to heat up food.
Okay. So what would be a tip from you if people wanted to start playing with HML? Let's say they just want to, we have a lot of people with the background of infrastructure who are working with Google Cloud itself, but they find it interesting and they want to start.
Yeah. Well, I highly recommend getting one of the Coral development boards, maybe this mini. It's my new favorite, so it's very cost efficient, very small, very power efficient, easy to use. Or if they want to use their laptop or maybe a Raspberry Pi that they already have, then this Coral USB accelerator is equally good. Or then, of course, the large dev board, which has a lot more memory and etc., can run bigger things. Anyway, get one of those prototyping things. Then I would recommend doing the same as me, so trying AutoML. Cloud AutoML is by far the easiest way of creating machine learning models. Export then the model to TensorFlow Lite, drop it here, and then you just buy some chickens, and then you make sure you can classify your chickens.
Yeah, it's pretty cool. I want to start myself because I started learning machine learning, but I think it would take me, to learn TensorFlow, and actually to train some models in TensorFlow. It would take me a year probably to get my hands on it. So yeah. I was thinking whether it's good enough to just use AutoML, create your models, and then put them on the. But it seems like that's the case. Okay,
yeah, just to let you know, the chicken classifier that I keep mentioning, because it's one of my latest things that I built, this in total took less than 2 hours. From the idea, of course, I had to buy the chickens, and when I got the chickens, less than 2 hours to the current demo state, which actually can classify usually the chickens. So less than 2 hours is pretty good time to prototype MVP.
Mm-hmm. Yeah, so maybe, and are there any tutorials on how to use AutoML, and what would you recommend?
Yeah, so all the Google Cloud services have the Getting Started pages, which have the Getting Started tutorials. I would start there. And also the Coral. So if you go to coral.ai, then the products have Getting Started guides, and they also walk through creating models and running pre-built models and running them on the device. So I would start there.
Yeah, that might be much easier than going through the all, terminologies of ML and learning it from scratch.
Yeah.
Okay, I see we do actually have a question from Vitold. Okay. How much time is the process taking on dev boards in Kyocera case study?
The pre-processing for the training images, I ran that on my Mac first, but then the pre-processing takes, if I don't remember now, 10 to 20 milliseconds maybe of cropping the image, and then the actual machine learning inference is only about 9 milliseconds.
Mm-hmm. So that's extremely fast.
Yeah.
Yeah, makes sense. Guys, do you have any more questions, or maybe someone has a really nice use case for Vision ML that you could use?
Then meanwhile, please also remember that even though I showed visual classification things here, you can do the same for sound. Well, you saw the sound example earlier, that live demo, but you can also do that for sensor readings. So we have now a lot of customer use cases where they connect high frequency sensor readings to a machine learning model like the HTPU. So the machine learning model or the neural network doesn't even know that an image is an image. It's just a stream of bits and bytes. So you can do the same for sensor readings, numerical data, time series data.
So you could actually, I'm just thinking about another use case where you can have a device, maybe a Raspberry Pi or this dev board, right, connected to a battery, and you can actually walk with it and perform predictions, right, of a live object. So I've seen a couple of...
This dev board mini is very, very low power.
Yeah. So having the possibility of having this, as a mobile device where you can walk with it, it's giving a lot of use cases. And I get this is getting more, the footprint of the device is getting smaller and smaller, right?
Yeah.
Exactly, yeah.
Here's the M2, and this one still actually is dependent on the M2 connector form factor. But then if those companies who manufacture products, physical products, they can literally just take the SOM, I believe, the HTPU chip itself and embed it on their motherboard. So it's even smaller than this.
Amazing. Okay, I see we have another question. What is the performance of AutoML versus custom build model in Tensor, for example? So I guess...
Of course, it always depends. It depends on your source data and what you do with it and how did the humans optimize their model. But of course, at Google, they've run a lot of testing. And nowadays, the kind of general consensus is that most of the time, AutoML can actually create a higher quality model than the humans could train. And one reason is that AutoML uses machine learning to create machine learning. So it's able to try weird combinations of hyperparameter tuning, whatever, that humans couldn't even think about. And it's able to try so many different things in parallel where humans have limited capacity to try things. So by experimentation and weird optimization, AutoML can usually actually reach a higher quality than humans.
And I guess AutoML, we can also save it as you were showing, right? We can save it to multiple endpoints, like, put it in a container or use the JavaScript. Yeah, so yeah, that's quite great. And it's actually, that's the good news, right? That we don't actually need to train the models yourself, and only if you have a good use case with the devices that are available there, you can...
it's really... I believe personally, and I try to demonstrate it in my day-to-day work, that it really accelerates from idea to prototype level at least, and then you take it from there, MVP and production ultimately. But it's really shortening the time, and like you said, democratizing applied AI, I guess, is really having your own custom AI that actually works for your product or service. You can get that working probably the same day as a prototype. So it's more, the limitation is more your imagination. So just yesterday, I published a YouTube video, just shamelessly plugging my video, where I built a sports analyzer. So I was flying a drone. Why? So because the drone has an automated camera that can follow me. So I was running and the drone was following me. And then I was analyzing the drone footage with the HTPU. And I was able to see that I'm actually overstriding. So when my foot hits the ground, it's landing in front of my body, which is bad. It's big impact to the knees, and it's slowing me down. So you can do crazy things like sports analyzers using the same technology with small tweaks.
Okay, I think let's answer the last question. There is a question related to how long did AutoML learning took in Kyocera case?
Yeah. If I remember right, that was about a year ago. I think it was training the model about 3 hours. But I tried to maximize everything, like give me the highest possible quality output, of course, for customer. Usually when I run AutoML, I've done dozens, at least 50 different AutoML models. Usually it takes something like 15 minutes, 30 minutes, something like that.
That's amazing. And the pre-processing itself, this is done using a Python on the chip, or this is a part of the model?
Yeah, so I can only code Python anymore. I forgot all my other languages. So for the pre-processing for Kyocera, I simply used very simple Python pillow image processing library functions. And first I ran it on my Mac, but then of course verified it on the dev board. But the dev board, Coral dev board, has a quite beefy CPU. It's a 1.5 gigahertz ARM quad core, so it's executing the Python quite fast.
So just to sum it up, you need to have hardware that will be doing the pre-processing using Python, right? And then you have the actual model that is run on the TPU, right?
Yeah, in this particular case, where we realized that pre-processing the data before training or giving it to the machine learning model gave a significant. So massaging the data sometimes can give you a significant improvement. Sometimes, like with this chicken detector, at least with the current version, it doesn't pre-process anything. It's analyzing the raw camera stream. So it's always use case dependent.
And this actually would bring the other question now. If you were showing us this awesome model where you can switch off your lights, you can turn it on. So for this one, are you using any libraries that already exist, any pre-trained model, or this needs to be trained from the scratch?
For that one, I used a Coral example. So hang on, let me try to find it. Give me just 1 second. Yes, so ta-da, here you go. So this is the one I used. So I used the DevBoard Mini. It comes with Debian OS pre-installed. I simply did a git clone from here, from GitHub, from this existing Coral example repository, which has the keyword spotter. So this one comes with a pre-trained model. So I simply use the pre-trained model, and it has a list of words that it can detect. Where are they? Here, the pre-trained model is trained with 148 phrases that it can detect. So for my light control, I just selected some of these, like switch on and switch off. I used a pre-trained model with existing keywords that it can detect, and then it was a matter of simple glue code with Python. I just implemented then the logic of sending a Python command to my lights, and that's it.
Okay, that's good news, because actually I was thinking about all those implementation of smart homes where you need to have connectivity to internet, right? So now you're independent to switch off your light.
Yeah.
Your internet connection is not on. Okay, great. That was great presentation again. I'm really amazed with how simple it is, to start playing with HML, even having no understanding of machine learning, the insights of machine learning. Yeah. So I'm really excited. I'm probably gonna start playing myself with it when I only get some time. I guess seeing the comments in the chat, I see a lot of people probably going the same way. So we have 7 minutes left, guys. If there are any more questions, just keep on putting them in the chat on YouTube, or you can contact us, and I guess we can actually come back to Marku and get the answers back. And I hope to see you, Marku, again in GDG, because that was I must admit, one of the most interesting sessions.
Oh, thank you so much. If you guys liked me, want me to come back, I'm more than happy to come back.
Yeah, and maybe if you can put the link to your channel on YouTube. I think this is yes. GCP Asia, right? APAC.
Give me a second. Let me send a link to my latest episode. I talked about the AI codes, which I literally published yesterday. So if I send it to you, Konrad, in the chat here, can you please send it to the folks, or?
Yeah, definitely. I'll do that. Okay, I have it. I'll put it in the chat right now so everyone has access to it. Okay.
So my episodes are basically trying to show the same thing, similar thing as you saw here, but other use cases. So why did I build something? How did I build something, and how it works? And I try to make them a little bit entertaining as well, so they're not so boring. No slides. Never any slides in my episodes.
Awesome. This is actually how I found your YouTube videos when I was learning for the machine learning exam. And I thought, oh well, it can be actually interesting, not only sort of learning TensorFlow libraries, but also you see things working in real life, and things being very simple. Okay, cool. So I think we'll wrap up. I'd actually like to finish today's meeting with a small contest. I hope you guys were paying attention today. I will ask one question, a very simple one, I think. So I will also put it in the chat, and the person that will first answer it is winning the hard copy of the book that will help you to prepare for the Professional Cloud Architect exam. So just put your answer in the chat. I'll ask the question right now. I know there is a small delay between our studio and YouTube, but let's try it. So guys, can you tell me what actually TPU stands for? Just put it in the chat in YouTube. Okay, let's see. There is like 10 seconds delay. Okay, or maybe I'll put the question in the chat as well. Okay, and I think we have the first answer. Let me just double check in YouTube. And we have Paweł Żukowski, and that's correct. Correct me if I'm wrong, Marco, but that's the correct answer, right?
For me, yes. Yeah, it's correct. It was scrolling bad for me, but yes.
Okay, perfect. Thank you so much for today, Marco, again. I hope to see you again in GDG Poland, maybe someday live.
Yes.
in Warsaw or in Bydgoszcz.
Absolutely. Love it.
And Paweł, please contact me on LinkedIn or via the GDG meetup page, so I can send it over to you. Thanks again, Marco. Have a great weekend, and thank you all for participating.
You too. Thank you. Bye-bye.